Hi, Stu Schwartz from MasterMathMentor.com. This is video BC07. The topic is Logistic Growth, and it covers the BC manual pages 35 through 37. In the previous video, we studied Euler's method, which was a way to approximate solutions to differential equations. Let's go back to actually solving them exactly. Exponential growth talked about growth of a population which is proportional to itself. So if P represents the current population and T equals time, then our differential equation was dP dt equals Kp. This was saying that the greater the population, the faster the population grew. There are many real-life examples of exponential growth. Populations, whether they be human or animal, spoilage of food, devastation from fire, smartphone sales, cancer cells, invasive species, microorganisms in a culture, the money you get from compound interest, and of course, the COVID-19 virus. As this video is being produced, the total coronavirus cases in the United States is still growing at an exponential rate. To solve the differential equation, we first separate the variables. We get dP over P equals K dt. We integrate both sides and get the natural log of the absolute value of P is equal to Kt plus C, giving us P equals e to the Kt plus C, which is e to the Kt times e to the C. And since e to the C is a constant, our formula is P of t is equal to C e to the Kt. The graph of the exponential growth curve is shown. How fast it rises is dependent upon the constant K. The greater K is, the faster the growth. If K is positive, then there's growth. If K is negative, then there is exponential decay. Assuming K is positive, the limit of P of t as t approaches infinity is infinity. Another type of exponential growth is called limited exponential growth. It is a situation where the growth of a population is proportional to how much room it has to grow. Suppose you are watching a National Hockey League game and the game goes into sudden death overtime. Suddenly the visiting team scores. The game is over. Everyone gets up to leave, and at first the rate of people leaving is very, very fast. But as time goes on, the rate of people leaving slows down. In limited exponential growth, P is the current population, T is time, and M is called the carrying capacity. In the hockey example, M would be the total number of people who are attending the hockey game. That is the maximum number of people who can leave the rink. So, since the growth of the population is proportional to how much room it has to grow, our differential equation is dP dt equals K times the quantity M minus P. To solve this differential equation, we divide both sides by M minus P and then integrate, getting the integral of dP over M minus P is equal to the integral of K dt. To make the integration easier, we will multiply both sides by -1 to get the integral of dP over P minus M equals the integral of -K dt. Integrating, we get the natural log of the absolute value of P minus M is equal to -Kp plus C. And therefore, we get P minus M is equal to e to the -Kp plus C, or P minus M is equal to e to the negative Kp times e to the C. And finally, our statement is P of t is equal to M plus C e to the negative Kt. The shape of the solution is shown where the growth is very quick at first and then levels off to the carrying capacity. The limit of P of t as t approaches infinity is no longer infinity, but is M. A third type of growth is called logistic growth. In logistic growth, the growth of a population is proportional to both itself and how much room it has to grow. As we saw with limited exponential growth, there are three variables: P, which represents the current population, T, which represents time, and M, which represents the carrying capacity. Since P is the current population and M is the carrying capacity, M minus P represents the room for growth. So the differential equation signaling logistic growth is dp dt equals Kp times the quantity M minus P. Sometimes K is a very small decimal. In order to make the equation look a little bit easier, we will take the M minus P and divide it by M, and take the K and multiply it by M. That does not change the equation. We are left with dp dt equals some constant times P times the quantity 1 minus P over M. We still use the variable K, but the constant is not the same constant as it was in the original equation. So on the AP exam, you are responsible for two differential equations that signal logistic growth. dp dt equals Kp times the quantity M minus P, or dp dt equals Kp times the quantity 1 minus P over M. We will not spend the time going over the general solution to this differential equation because you are not responsible for it. But you are capable of understanding it because everything has been covered. The technique uses partial fractions. Our final answer is that P is equal to M over 1 plus C e to the negative Kt. You are not responsible for this formula. In an AP problem, it will generally be given to you. This is the typical graph of a logistic growth equation. Notice at first the rate of change is very small, but then it increases, and at a certain point gets fairly steep. But then it starts to level off to the carrying capacity. The general shape is an S-shaped curve. A classic example of logistic growth is rumor spreading. Rumor spreading involves two types of people: tellers who know the rumor and hearers who do not know the rumor. At first, there is only one or very few tellers and a lot of hearers. For instance, in a building where rumor is spreading and there are 100 total people, let's suppose that there is one teller, 99 hearers. We look at the product of those numbers and we get 99. As tellers talk to hearers, the hearers now become tellers. So we then move to 10 tellers and maybe 90 hearers. The product is 900. The number of tellers will go up, the number of hearers will go down, and the product will go up. However, as time goes on, there will be more tellers than hearers, and the product goes down. Towards the end of this rumor spreading, there are 95 tellers and the hearers are only 5. So the product is 475. Problem 1 has a school with 1,300 students where 25 of them start a rumor that the school is going to be replaced with a new one. One day later, 65 students know the rumor. Part A asks to write the differential equation that describes the situation, solve it, and then determine how many students have heard the rumor after 7 days. Rumor spreading signals logistic growth, with our carrying capacity to be 1,300. So our differential equation is dP dt equals Kp quantity 1,300 minus P. And we know that this will translate to the solution P is equal to 1,300 over 1 plus Ce to the negative 1,300 Kt. Our job is to find both C and K. When T equals 0, P equals 25. So we set 25 equal to 1,300 over 1 plus C, getting C plus 1 equals 52 and C equals 51. When T equals 1, we know that P equals 65. So 65 equals 1,300 over 1 plus 51 e to the negative 1,300 K, or 1 plus 51 e to the negative 1,300 K equals 1,300 over 65, which is 20. That gives 51 e to the negative 1,300 K equals 19. We then divide both sides by 51 and get e to the negative 1,300 K equals 19 over 51. At this point, we could solve for K, but since our equation has an e to the negative 1,300 K in it, we simply substitute 19 over 51 for e to the negative 1,300 K, and we get P of T is equal to 1,300 over 1 plus 51 times 19 over 51 raised to the T power. To find how many students know the rumor after 7 days, we simply plug in 7 to that equation and we get 1,237 students. Part B asks how many students know the rumor when it is spreading the fastest. Since the differential equation dP dt equals K times 1,300p minus p squared, we want to maximize dP dt, which means taking the derivative of it and setting it equal to 0. So the second derivative, d squared p over dt squared equals K times 1,300 minus 2p times dP dt. We know that dP dt is not equal to 0, so 1,300 minus 2p has to equal 0, or 2p equals 1,300, and p is equal to 650. Notice that 650 is exactly 1/2 of 1,300. That's not a coincidence. In logistic growth, the fastest spread will always be at 1/2 the carrying capacity. Part C asks how long will it take for the rumor to spread the fastest. We know that 650 people will know the rumor when it is spreading the fastest, but that does not tell us when that happens. In order to do that, we will set our equation 1,300 over 1 plus 51 times 19 over 51 raised to the t, and set that equal to 650. Solving that, we get 1,300 over 650 is equal to 1 plus 51 times 19 over 51 raised to the t. And therefore, since 1,300 over 650 is 2, we get 51 times 19 over 51 raised to the t is equal to 1, or 19 over 51 raised to the t is equal to 1 over 51. Taking the natural log of both sides, we get t natural log of 19 over 51 is equal to negative natural log of 51. And our answer is t equals negative natural log of 51 over the natural log of 19 over 51. And using a calculator, that turns out to be 3.982 days. This point, 3.982, 650, is the point where the rumor curve is spreading the fastest. Graphically, it is where the curve switches from concave up to concave down, which we know is the inflection point. We see by the graph the telltale S-shape of the logistic curve with the carrying capacity of 1300. We also see that almost 4 days in, 650 students know the rumor, and that's when it is spreading the quickest. Problem 2 reads, the growth of the percentage of algae on the surface of a lake is proportional to the current percentage of algae on the lake and the percentage of the lake not yet affected. On June 30th, the surface of the lake is 20% algae, and on July 15th, it has gone up to 25%. We want to determine the day when the lake will be 90% covered. As imposing as this solution looks, there's only a slight bit of calculus in it, and that is in the first step. We are told that the rate of growth of algae is proportional to the current percentage of algae and the percentage of the algae not yet affected. That makes dp dt equal to kp times 100 minus p. We use 100 to represent 100%. And we know that that gives the equation p is equal to 100 over 1 plus c e to the negative 100 kt. Now we plug in our points. When t equals 0, p equals 20. So we get 20 is equal to 100 over 1 plus c, and therefore c plus 1 is equal to 5, and c is equal to 4. When t is equal to 5, p is equal to 25. So we get 25 is equal to 100 over 1 plus 4e to the negative 500k. That gives 1 plus 4e to the negative 500k is equal to 100 over 25, which is 4. That gives 4e to the negative 500k equals 3, and e to the negative 500k is equal to 3/4. Unfortunately, our original equation has an e to the negative 100k, not e to the negative 500k. So we raise it to the 0.2 power, and therefore we get p of t is equal to 100 over 4 times 3/4 raised to the 0.2t. If you have a calculator to confirm your answer, I suggest that you graph this function to make sure that it makes sense. We can see the logistic curve and the asymptote at 100. We are now interested in where this equation is equal to 90. So we set 100 over 1 plus 4 times 3/4 to the 0.2t equal to 90, giving 1 plus 4 times 3/4 to the 0.2t equal to 10/9. That gives 4 times 3/4 to the 0.2t is equal to 1/9, and 3/4 to the 0.2t therefore is equal to 1 over 36. And taking the natural log of both sides and doing some algebra, we get t to be negative natural log of 36 over the natural log of 0.75, all divided by 0.2, which is 62.283 days. Since June 30th is day 0, July 1st would be day 1, and since this is going to take 62 days, this will happen on September 1st. Again, I suggest that you confirm your answer graphically by graphing y is equal to 90 and finding where the curves intersect. And notice that it is at the point 62.2890. Problem 3 reads, the population of beavers in a park changes according to the semi-logistic equation dB dt equals k times quantity b minus 80 times quantity 240 minus b. The slope field is given below. What are all the possible values for the limit as t approaches infinity of b of t? And we also would like to find b when growth is a maximum. This is the type of problem you could see on the AP exam because it requires a little bit of thinking. The given differential equation is not quite in the form of a logistic differential equation. As we look at the slope field, we realize that there are 5 possibilities for the initial value of b. The first is that since b has to be a positive number, b could be less than 80, b could equal 80 exactly, b could be somewhere between 80 and 240, b could be exactly 240, or b could be greater than 240. Let's examine each of these possibilities. Suppose the initial number of beavers is less than 80. As we can see on the slope field, the population of beavers dies out. And since the number of beavers cannot be negative, the limit of b of t as t approaches infinity is equal to 0. Suppose the initial number of beavers is exactly 80. Then the limit of b of t as t approaches infinity is equal to 80 as dB dt is equal to 0. Following the slope fields, the number of beavers stays consistently at 80. Suppose the initial number of beavers is a number between 80 and 240. Then the number of beavers grows according to our logistic S-shaped pattern, and therefore the limit of b of t as t approaches infinity is equal to 240. Suppose the initial number of beavers is exactly 240. Then our slope field shows that the number of beavers will not change, and therefore the limit of b of t as t approaches infinity is equal to 240 because dB dt is equal to 0. Finally, suppose the initial number of beavers is greater than 240. Then by the slope field, dB dt will be negative, and the limit of b of t as t approaches infinity is equal to 240. Shown are all 5 possibilities on the slope field. The second question is to find b when growth is at a maximum. Since it appears that for most cases the curve levels off at 240, you might think that growth is at a maximum at half of that, or 220. That is not true. There is only one situation when the growth of beavers is positive, and that's when the initial population is between 80 and 240. So we look at dB dt in that range, multiply out, and we get k times 320b minus b squared minus 19,200. We want to maximize that, so we take its derivative and we get k, 320 minus 2b dB dt is equal to 0. And that gives us 2b equals 320 and b is equal to 160. So when b is equal to 160, we have the growth is at a maximum. If the initial population of beavers is greater than 160, then the greatest growth rate will be whatever that initial value of beavers is. Number 4 reads, when a new computer operating system comes out, it is known that 30% of users will not upgrade. The percentage P of people who will upgrade spreads at the rate dp dt equals 0.2p times the quantity 70 minus p, where t is measured in years. The operating system was pre-released, and 5% of users are already using the operating system at the time of actual release. We'd like to know at what month after the operating system comes out will the spread of the operating system be at a maximum if Euler's method is used to approximate the solution to the DEQ. This is another non-traditional problem. It tests your knowledge of logistic growth as well as Euler's method. First, the equation signals logistic growth, and that means that the carrying capacity is at 70%. And when the percentage of users who will upgrade is at 35%, that will be when the rate is growing the fastest. We want to find that time. We apply Euler's method by making a table with 4 columns, T, P, dP dt, and dP. Since T is measured in years, but we want to work in months, our values of T will be 0, 1/12, 2/12, and 3/12. Our initial value is when T equals 0, P is equal to 5. Therefore, dP dt by the formula is equal to 65, and therefore dP is 65 times 1/12, which is 5.42. The second row, P becomes 10.42. dP dt will follow the formula, and dP will be whatever dP dt is times 1/12. We continue this down for 4 rows, and we see that when P gets to 37.72, we know that it must have passed 35. So we find that the time of fastest growth must be between 2 months and 3 months. It appears it'll be closer to 3 months. Shown on the screen are 3 examples we used earlier of exponential growth: population, fire, and food spoilage. But are they really examples of exponential growth? In the case of population, we can have exponential growth for a time. However, realize that food will run out. If we're talking about the population of a neighborhood, it can get crowded very quickly, but then people will stop moving into it. So population will only be exponential for a while. In the case of fire, destruction can occur at a devastating rate. But eventually everything is going to be burned and there will be nothing left to burn. At that point, the fire must die out. In the case of spoilage, mold will appear all over your bread and spread very quickly at an exponential rate. But when all the bread is gone, there's nothing left to spread. Exponential growth cannot continue forever. The graph on the screen shows the growth of COVID-19 in the early days in mainland China. The blue dots represent time versus the number of cases. It appeared that COVID was spreading at an exponential rate. However, it is impossible for it to spread at that rate forever. Eventually, everyone gets it, and therefore it cannot spread anymore. The green curve shows an exponential model based upon those points, while the red curve shows a logistic model based upon those points. It appears that the curve has hit its inflection point and is starting to level off. But the world does not run on mathematical formulas. The only way to know whether this curve has hit its inflection point and is beginning to become concave down and level off is to look at it much, much later. We have no idea at this point whether the growth of COVID in the United States has truly begun to level off. The calculator can help us make decisions based upon the past. We take the data, x, y, and put it in our lists, L1 and L2. X cannot be 0. If you have 0 data, change it to 0.01. And then from the home screen, go into your Stat Calc menu and choose Logistic Y1. That will do logistic growth and place the result in Y1. The more points you have, the better your model will be. In this case, we ended up with a formula that says cases equals 48,442 over 1 plus 111.567 e to the negative 0.2929 times day. That was based upon the first 18 days of data. And it would show that it would level off at 48,442 cases. That prediction turned out to be inaccurate. As of now, there are approximately 84,000 cases of COVID in mainland China. That is based upon the most up-to-date information available.